Hello everyone, my name is Sahand and I'm going to present our paper titled Learning the Latent Space of Robot Dynamics for Cutting Interaction Inference. This is the work that I did as part of my master's under the co-supervision of Professor Ina Sharf and Professor David Meger at McGill University. In this work we use variational autoencoders to learn the dynamics model of a robotic arm. We further show that its latent space has expressive representations of robots' interactions, allowing us to infer and classify these interactions. We evaluated our approach in the particular case of robotic woodcutting task on a real experimental setup. This application has been largely motivated by the automation needs in the forestry operations. The need for automation from different aspects such as perception, planning, and control in timber harvesting operations is evident. This is mainly due to the safety concerns and suboptimal productivity of such operations. In this work, we tackled the problem of robotic woodcutting and manipulation. Forestry machineries are often equipped with heavy-duty and sophisticated robotic arms, with complex dynamics and even more complicated environmental interactions. There's also a wide variety of tree species in different sizes and shapes that makes the woodcutting and manipulation even more challenging. We therefore propose a dynamics model learning framework that is capable of both learning the dynamics model and inferring such complex interactions. The rigid body dynamics of a robotic manipulator can be defined as this equation, where Q is the joint positions vector and F is the interaction force. On the left-hand side, we have inertial terms, Coriolis terms, and the gravity terms. While on the right-hand side, we have joint torques, joint frictions, and the Jacobian matrix multiplied by the interaction force. In the case of cutting dynamics, the interaction force can be approximated as a spring damper system of this form. This includes a proportional term based on the end effector position and the derivative term based on the end effector velocity. However, the equation has multiple unobservable parameters that depend on many properties of the environment, such as the material, thickness, and shape of the object being cut. But these values can be captured by the latent space as shown in our evaluations. The goal in this work is therefore to learn the dynamics model of a robotic cutting and use its latent space to infer robot interactions. The latent space is learned by reconstructing the state history as well as predicting the next state. The figure here shows the overall diagram of our approach. First, we collect sensory data from the real robot performing a woodcutting task. We then learn the latent space through reconstructing and predicting the states. Then the network is frozen and its latent space alongside the interaction properties are used to train the classifier that infers the robot's interactions. We use generative latent variable models to learn the robot dynamics. These models learn the joint distribution of both the states and unobservable states as shown in this equation. In particular, we use variational autoencoders, also called VAEs, and Vector-Quantised variational autoencoders, or VQVAEs, as they are both inherently strong in learning meaningful latent representations. The main difference between the two is that the latent space of the VAE is continuous, while the latent space of the VQVAE is discrete. As shown in the results, the discrete latent space can be useful in some cases. This is the network architecture that we used. The input to the model is a history of joint states over a specific window size, and the output is the reconstruction of this history alongside the prediction of the next state. The state here is defined as joint positions, joint velocities, and joint torques. However, for the predictions, the state includes only the positions and velocity, as the torque is considered the control input. We evaluated a model on a real experimental setup using Canova JK2 robot with 6 degrees of freedom. We designed a custom end effector fixture for holding the cutting tool, which is a circular saw. We also designed a specimen fixture with an integrated force-torque sensor for holding the wood specimen. However, the measurements from the force-torque sensor have not been used in this work because integration of sensors on the end effector of a timber harvesting machine is highly challenging. We collected a dataset of 180 cuts on 12 wooden specimens with different materials and thicknesses. The table here shows the availability of the materials across different thicknesses. Our dataset is also publicly available at the following address here. The video shows a few examples of the cutting episodes. First, the robot starts moving from an initial configuration towards the specimen. Once the cut has been made, the end effector is redirected to its initial position and gets ready for the next cutting episode. We evaluated our approach from two standpoints: performance of interaction inference and forward prediction. For interaction inference, we evaluated three cases: cutting detection, material classification, and thickness classification. The figure here shows a qualitative analysis and visualization of the latent space. The green dots are active cutting, and the blue dots are free motion of the robot. As it can be seen here, there is a distinct separation between the two in the latent space. For interaction inference, we compare the F1 score across different sizes of the latent space. F1 score tends to combine both precision and recall in a single performance measure and is thus a good comparison criterion. The baseline here is a classifier trained on the raw state space and is plotted as the black dashed lines. Results shown here are obtained on the validation set of our dataset. The left column shows the results obtained with the VAE over the latent space dimension. We used 4 different values for the KL regularization term and changed the dimension of the latent space from 2 to 32. Results show that even though their performance is changing slightly across different KL weights, they have increased with the size of the latent space. In many cases, even with a small latent space dimension, such as 4, the model is already outperforming the baseline. The right column shows the VQ-VAE results for a range of embedding dimensions in numbers. The baseline is the same as before and is shown as the flat surface. Here, we changed the number of embeddings and their dimensions from 2 to 16. As it can be seen, in many cases, the models are able to outperform the classification performance of the baseline, even with a low number of embeddings and dimensions. This in fact shows that the latent space has expressive representations of robot interactions. To sum up the results for interaction inference, we choose the best model from the validation set and compare its performance on the test set with that of the baseline. The best performance models are highlighted for each row. As it can be seen here, the results are significantly improved with VAE and VQ-VAE models. In particular, the VAE model has the best performance for cutting detection and thickness classification, while the VQ-VAE has the best performance for material classification, which is an inherently discrete task and therefore more in line with its discrete embeddings. We now compare the performance of the forward predictions. The baseline is a recurrent neural network, namely an LSTM trained on the raw state space, and is shown as the black dashed line. The figure on the left shows the results obtained with the VAE, and the figure on the right shows the VQ-VAE results. Although the LSTM is outperforming both methods, the VAE still has a competitive performance even though it has far fewer parameters and no recurrency in its architecture. This shows that not only are the latent variable models suitable for interaction inference, but also they have a good performance in forward predictions of complex dynamics. Finally, we take the best models from the validation set and compare their results on the test set. Again, the results indicate competitive prediction performance of VAE model compared to the LSTM network. The best VAE model has 11 dimensions in its latent space, and the best VQ-VAE model has 2 times 10 embeddings. Both are significantly smaller than the original state space. To conclude, first, we showed that the latent space of robot dynamics with complex cutting interactions can be learned directly from raw sensory data over a window of time. Second, we showed that this latent space is expressive enough to allow for robot interaction inference and classification of cut properties. Finally, we showed that VAEs and VQVAEs have competitive forward predictions performance compared to RNNs in interaction-rich environments, while providing more interpretative information through the latent space. Thank you very much for watching this video. Please check out our paper for more details and more experimental results. And please do not hesitate to contact us if you have any questions. Thank you.